Cosmic collisions involving stars and black holes are not mere accidents in the vast arenas of space. They are powerful events that shape the structure and evolution of the universe. These cataclysmic events provide astronomers with crucial data to understand the life cycle of stars and the mysterious nature of black holes. Understanding these collisions helps us appreciate not just the scale and power of cosmic phenomena, but their fundamental role in sculpting the observable universe. Through the study of these events, astronomers can peel back layers of cosmic mysteries, offering insights into the very fabric of reality. When stars collide, the universe holds its breath, witnessing a spectacle of unimaginable scale and energy. These collisions can result in the formation of a new star if the stars merge, or a binary system if they manage to survive the encounter. The outcome greatly depends on the mass, speed, and angle at which the stars collide. A direct collision typically results in the merging of stars, creating a single larger star. In contrast, a near miss might lead to the formation of a binary system, where both stars, caught in each other's gravity, continue to orbit around a common center. These systems can be stable for millions of years or lead to further cosmic events. Gravitational waves, first predicted by Einstein, have opened a new window into observing the universe. These ripples in the fabric of space-time are generated by some of the most violent and energetic processes in the cosmos, such as the mergers of black holes or neutron stars. Detecting these waves requires incredibly sensitive and sophisticated instruments. When these waves traverse the Earth, they stretch and squeeze space itself, albeit minutely, allowing detectors like LIGO to measure these distortions and thus listen to the symphony of the cosmos. In the realm of cosmic collisions, supercomputers play the role of cosmic seers. These powerful machines simulate scenarios that are impossible to set up in any laboratory or observe directly in many cases. Through these simulations, astronomers can predict the outcomes of stellar collisions and the complex dynamics of black hole mergers. For instance, simulations have shown how the orbits of stars around black holes evolve, leading to either eventual ejection or spiraling doom towards the black hole. These predictive models are crucial for understanding the range of possibilities in the chaotic environments of deep space. Black hole mergers, the powerhouses of the universe. Black hole mergers are among the most powerful events in the universe. When these titans of mass and gravity come together, they do not just merge, they release energy in the form of gravitational waves that can be detected across galaxies. The merger process involves complex dynamics, where the black holes lose energy through gravitational radiation, drawing them closer until they finally coalesce. The final black hole that forms is less massive than the sum of the original masses, as energy has been radiated away in the form of gravitational waves. Neutron stars, the densest objects in the universe. Neutron stars are the remnants of massive stars that have undergone a supernova explosion. They are incredibly dense, with masses comparable to that of the Sun, but compressed into a sphere only about 20 kilometers in diameter. When two neutron stars orbit each other, they emit gravitational waves and lose energy, gradually getting closer until they collide. This collision can result in various outcomes, including the formation of a black hole, a more massive neutron star, or a spectacular explosion known as a kilonova. Tidal captures and their consequences. In the dance of gravity, not all encounters lead to a merger. Tidal capture occurs when a star or compact object passes close enough to a black hole or neutron star to be caught in its gravitational field, but not immediately swallowed. This process can lead to the gradual spiral of the star into the denser object, emitting high-energy X-rays and other radiation. This gravitational interaction significantly affects the captured body, often stretching and distorting its shape due to the intense gravitational forces at play, a phenomenon known as tidal deformation. The observation of gravitational waves has revolutionized our understanding of the universe. Each wave carries information about its origin, such as the masses of the colliding objects and the nature of their merger. The detection of gravitational waves from events like GW 150914, where two black holes merged, has provided direct evidence of black holes' existence and properties. These discoveries are not just scientific milestones, they are stepping stones that could lead to a deeper understanding of gravity, quantum mechanics, and the overall structure of space-time. The Laser Interferometer Gravitational Wave Observatory, or LIGO, is a marvel of modern physics and engineering. It consists of two enormous laser interferometers located thousands of miles apart, which can detect changes in distances less than 1,000th of the diameter of a proton. Other detectors like Virgo in Italy and GEO 600 in Germany complement LIGO, helping to pinpoint the origin of gravitational waves more accurately. These collaborations are crucial for the continued success and accuracy of gravitational wave astronomy. While gravitational waves provide one lens through which to view cosmic collisions, electromagnetic observations offer another. In 2017, scientists observed both gravitational and electromagnetic signals, light, from a single event, a neutron star collision. This dual observation, a first of its kind, opened up a new field of multi-messenger astronomy, providing a more comprehensive picture of these cataclysmic events. This synergy between different observational platforms allows astronomers to validate their findings and gain a fuller understanding of the processes at work. Kilonovas, the aftermath of neutron star collisions. Kilonovas are massive explosions that occur when neutron stars collide and merge. These events are incredibly bright, often briefly outshining entire galaxies. They are also key sites for the production of heavy elements like gold, platinum, and uranium in the universe. Observations of kilonovas provide crucial data on the synthesis of these elements and the physics of extremely rapid and intense collisions. Neutron star mergers are not just spectacular shows of nature, they are also prime events for theoretical physics research. They provide insights into the behavior of matter under extreme pressures and densities and help refine models of atomic nuclei and the forces that hold them together. These events might also shed light on the elusive nature of dark matter and dark energy, potentially contributing to a unified theory of the fundamental forces of the universe. The field of cosmic collision research is rapidly evolving, with new technologies and missions on the horizon that promise to unveil further mysteries. Upcoming space-based observatories and more sensitive ground-based detectors will provide even more data on gravitational waves and electromagnetic counterparts. This advancing frontier of astrophysics not only deepens our understanding of the cosmos, but also continually challenges and enhances our technologies and methodologies. Cosmic collisions, from star mergers to the coalescence of black holes, compose a symphony of astronomical events that underscore the dynamic and interconnected nature of the universe. These phenomena, violent and beautiful, are not just distant spectacles. They are fundamental processes that shape the cosmos, influencing the structure of galaxies and the evolution of stars. By studying these events, we not only broaden our knowledge of the universe, but also deepen our appreciation for the intricate and majestic ballet of celestial dynamics. As we continue to explore these cosmic phenomena, we remain ever in awe of the universe's vastness and the elegant laws that govern it.